Hello there. We're going to do a homework problem using Desmos. And yeah, let's take a look. This is question number 8 from section 3.4. And then it says the curve is defined to be this. R of t is equal to this complicated looking thing. The good news is that it's in 2 dimensions. The bad news is that's sine and cosine, and so taking the derivative of these things will require product rules. Second derivative will require more product rules and a lot of simplifying and stuff like that. So I'm going to show you a way to do it using Desmos 3D. So let's get to Desmos. I'm going to view this so that it's like just the 2-dimensional view. And I can even set up the perspective here so that it looks like it's just flat on 2 dimensions. And that's all we really need. And for this to be effective, what we're going to do is we're going to define our function. Just a quick look again. It's negative t power. And then we have a cosine t. And then our second function, is going to be e to the regular t, and then this is multiplied times sine t. All right, we want to make this into a vector valued function as a function of t, and this is what we have. We're going to go from we're going to want to look at what happens at 2 pi, or I'm sorry, at pi over 6. So that's going to be our a value. So this is a parameterized curve. I can, make it go from -1 to 2 to see how it might look like. I think going from 0 to 1 is fine. Oops. Let's go from 0 to 1. And I'm going to be interested in seeing this at a specific point, and so let's get a slider going. We actually don't need the point. In fact, we want to fix it at a particular point, so let's go ahead and put in pi over 6 here. So this is where we want to be at that value. So if you want to label this, you're at the point 0.5 comma 0.8. So you're at that point over there. And then from here, we're going to create some values. Now, these things will be useful for us later on. And since this is an actual point, I'm going to call this P, just to give it a name because we'll access it later. And maybe I think I want to change the color of this and this to be both gray, because we're going to throw in a whole bunch of other things there. All right, the next step is to find our derivative, and our derivative is literally just the prime of this thing, and we do want to evaluate it at pi over 6. So I'm going to copy and paste this, so I'll have f prime of a and g prime of a, and now I get a point. Now that point is not meaningful to me because I want to consider this as a vector. Now this is velocity, so I'm going to label it v, and I'm going to put a subscript because we're going to use other v's here as well. And so this is v sub r to tell me that this is the velocity of the r function. Okay, now to actually create a vector, we type in vector, and then we need the starting point, which is going to be at the point, and then where the ending point is going to be the point plus that vector that we just found, v sub r. And so now we see this blue vector as our tangent vector at that point. So we don't need this anymore. You can imagine a vector from the origin to this point would be exactly the same as that vector that's been offset. So let's take that away. All right, next is our acceleration vector. And just like I labeled this v sub r, I'm going to label the acceleration vector a sub r. and then that's going to be this thing, except instead of the first derivative, I will have the second derivative. So to get the second derivative, you hit the single quote twice, and then we have the second derivative. So we have the same issue here. We just get a random point out in space somewhere, but we don't want that random point. We want to actually create a vector. So we'll type vector and then p comma p plus the a sub r vector that we just found. So this is our acceleration vector, the vector in purple. And we won't need this anymore, so we have our velocity and acceleration vectors. Okay, now that we have that, we're going to want to find our unit normal vector. So by the way, these are vectors, so I'm going to label, this is the velocity vector, so I'm going to label this as v sub v. And so the first v is going to be the velocity, and then the second v stands for vector. And this is our acceleration, so I'll label this as a sub v equals. So this is going to be our velocity vector. And we'll use that, we can use this later because Desmos allows us to do dot and cross products of these vectors. It's kind of neat. Okay, so now you have your velocity and acceleration vectors. We want to first find our unit tangent vector. So to find our unit tangent vector, we need to create it. It's essentially the velocity vector divided by its magnitude. So I'm going to take that velocity vector and then I'm going to divide by its magnitude. So its magnitude, I don't know if we can do this magnitude business. Looks like we can. So the single bars, remember, it's like absolute value, but if you're using it on vectors, it's like finding the magnitude. Now, again, this point is not going to be of any meaning, but this is the vector, unit tangent vector, capital T. So we can call it capital T. And then let's actually make it into a vector, which means it should be a vector from this point P. So I'm going to call this T sub V, like I've been calling all the others before. And this is going to be from the point P, and then P plus the T that we just found. Maybe I need to call this T sub R. And then call this T sub R. Oops, I'm sorry. I didn't need to call it T sub R, but I do need to say vector here. So this is the vector. Now that's the red vector, hard to see. So what I'm going to do is I'm going to change this vector to just make it a little bit thinner by changing the lines to 0.5 width. And then now I can see this a little bit better, and if I want to see it a little bit clearer, I could do a 1.5 width to make it wider. I don't need this point anymore because remember, this is the T unit tangent vector that we got. Alright, now to find a unit normal vector, what we want to do is we essentially want to take this and switch it around, and then take the dot product so that the dot product's equal to 0. So I'm going to copy this whole thing, and then I'm going to call this capital N. And then now the key is that if we switch the F prime and the G prime, switch those places and then even make one of them negative, which is what we're going to do, then the denominator should still be the same. So I'll make this into a G and I'll make this into an F, and then I will get another point here. Now the question is, do we want a minus sign in front of the F or in front of the G? So let's put it in front of the F for now. And again, this point here is not useful for us, but if we make it into a vector, so n sub v now is going to be the vector from the point that we're looking at, and then to the point plus the n sub r that we're negotiating right now. I'm going to do this in red as well. And what I'm noticing is that, oops. What I'm noticing is that the normal vector is going in the same side as, oops, same side as the acceleration vector, which is what I want. Now, had I initially put the negative in front of the G, then my normal vector is going to be on the opposite side of the acceleration, and I don't want that. I want the normal vector to be on the same side as the acceleration. So I'll take this out again and put the negative in front. So that's how you can find your perpendicular vector in 2 dimensions. In 3 dimensions, you won't be able to do this because it'll be too difficult. Because there's an infinite number of normal vectors in 3D, but in 2D there's only 2 choices, and so the choice is putting the negative sign on one or the other. Okay, so now I have this vector. I'll make it a little bit thicker. So I have my normal and the tangent and normal vectors. Now I want to find a of t. And a of t is just a projection of a onto t. And so remember, the projection involves a dot product. So if I project a onto t, it's like taking the dot product of a onto the tangent vector, the unit tangent vector. And since this is already a unit tangent vector, we don't have to divide by the magnitude of the unit tangent vector, because that's just equal to 1. So I'm going to call this a sub t, and that's going to equal to, now we actually want vectors that we're going to dot, so it's going to be the a vector, that's the acceleration vector, and dotted, so that's just the multiplication symbol, and then the t sub v vector, and then you'll see this length here. Okay, so now that we have that, that's going to be your a sub t, and then your a sub n is going to be similarly the acceleration vector dotted with the normal vector. And this should be sub v here. Okay, so there is our lengths. To verify this, I want to just to show you how this is actually working. This is the number that we're going to multiply the unit tangent vector by, so that we can stretch it, and then that would make your unit normal vector. So just to show you this, I'm going to draw a vector from the point to the point plus a sub t times the n sub v. So so a sub t is this, n sub v, I'm sorry, this is t, this should be t sub v. And something's wrong. Oh, I'm sorry. It has to be t sub, this is a vector, and putting a vector here, it's kind of weird how Desmos is working this out. This should be sub r. And what I'll do is I'll make this a different color. And that's to say that if we were to project the acceleration vector onto the extended tangent vector, it's going to be a sub t is going to be the scalar to project that. Okay, similarly, we can create a vector from P to P plus, now it's going to be a sub n times the normal vector, and this is going to be sub r. And I'll change the color of this to orange as well, and so you can see that that projects down here. Okay, so so that's it. And then if you were to take a sub t and a sub r, that should be your acceleration vector. So I'm running out of letters, so I'm going to call this a sub z is equal to a sub t times t sub r. Maybe I'll say t sub v. I think I can do the vector. Plus a sub n times n sub v. Nope, it doesn't look like I can do the vector, so I have to use the r's for now. And it still doesn't like it. What's going on? I put a little space here in the t. I don't know if that's going to make a difference. There it goes. And if I make a vector here from P to P plus a sub z, and change this color to orange again, I can see that that is exactly the acceleration vector. Okay, we can draw parallel lines over here to actually make a rectangle that would create this this relationship. All right, so that's it. The values here are, by the way, should be consistent. We have the point is given by these values, and the velocity vector is given by these values. This is the acceleration vector, which should be the same as the number that we got below here, which is the acceleration. We found the unit tangent vector, and we also found the unit normal vector. And if you look at the unit tangent vector and the unit normal vector, and you take the dot product, you should get 0 because they're perpendicular. We found the value for the scalar a sub t. That's the tangential component of the acceleration, and we found the scalar value for a sub n. That's the normal component of the acceleration. All right. Okay, so I hope this helps. Good luck.